So there's a slight change of plans. And since we saw that many of you have been pondering about exercise 5 and 6, I thought of using some of the lecture today to look at these exercises. And then Friday, we will now dedicate it more and more of the Fridays just to solve problems. And these problems are problems linked with a theory, which we go through every week. And these problems obviously in the exercise sets or will be the midterms. And in that way, we can discuss more about what does the physics mean, how do we solve these exercises, how do we get started. And the aim on Friday is more to look at exercises 5 and 6, because as we also mentioned previously in the week, exercise number 6, if you code that one, what you will see throughout the semester is that essentially you will end up making changes to that kind of program. And it's also a nice exercise, exercise 5. You've probably seen that you have the solution in a textbook. There's also essentially a solution in the lecture notes from week 3. So you can look it up and just test your own capabilities when it comes to integrate. But what I want to do first today is to try to say something about the angular momentum as well, and remind us a little bit about what we did on Monday. So we need some basic theory, and so that we can reuse some of these things next week, and also bring in some new important aspects of conservative forces, which are many of the fundamental forces in nature are actually conservative forces. So let's bring up the whiteboard and finish the exercise which we did last time. So we were looking at a simple example. So I just wanted to bring that one up. And then we try to wrap it up. So this is also an example of a conservative force. And you're going to meet this problem again in homework number 5. Not the one for next week, but the one for the week thereafter. And this is a typical problem which you may encounter. And the example which we had was that of an object. In this case, it could be an electron. And we had an electron which started at x0. So we know that one. And we could fix that one to, let's say, 0 meters. It has an initial velocity, which is also known. So we could just say that that is also 0. This is just to simplify the calculations. And then what we can use now is the work energy theorem to find the final velocity at the position x1. And in this particular case, what we have is that v1 is an unknown quantity. And we want, instead of integrating up, finding the acceleration, we now actually want to use the work energy theorem as an alternative to find the velocity at the final position x1. So this is just to show you how you can solve the same type of the problems, but with different means. And in this particular case, what we had now was a system which is supposed to mimic the surface of a material. So you could now think that you have atoms on the surface here, and they have a distance which we just call for b. So they're equally spaced atoms. This is pretty normal in a solid and in a material. And what you would have is an electron which is coming in here. It has a certain velocity, or just get kicks at x0. And so we have an E minus here. And this is being affected by a force, which is now an effective force, which is set up by these atoms. And since these are equally spaced, what we're assuming now is that this force has some kind of sign behavior. So this is a sine function, and it goes like 2 pi times x divided by b here. Now, how realistic that force is something which we will leave to people who do material science. But we're just taking this as an example of what is going to be a conservative force. If you calculate the curl of that one, you will find that the curl is equal to 0. And you see also that it depends only on the position. So that means that if we now want to calculate the final velocity, we are going to use the work energy theorem. And with the work energy theorem, we can then find this final velocity. So we would have the difference between the kinetic energies in the final position and in the initial position. And I just put that one to 0 in the beginning, the V0. And this is now equal to an integral with minus x0 up to x1. And then we have an f0 of a sine 2 pi. You will probably notice that my S's, my different letters S and R, are not very nicely written. So this is supposed to be an S, what you have here. So this is a sine function. Just imagine it is an S. Okay, I apologize for my bad handwriting here. So we make a typical change of variables, and I guess you're pretty familiar with that. So it means that we would introduce a new variable, which is simply 2 pi times x divided by b. That means that du becomes equal to 2 pi times dx. So we make the substitutions then. So we find the value for dx. So that means that we get a constant, which is equal to b divided by 2 pi. So when I then integrate with this change of variables, so let's put this in parentheses, then this is just going to be equal to an f0 times b. And then we know that when we integrate sine, we get minus cosine. And since we had minus in front of the integral, it becomes plus cosine. So we would have a cosine of 2 pi multiplied with the final position divided by b. And this is minus a cosine of 2 pi of x0 divided by b. And since we put x0 equal to 0, this is a cosine of 0, which gives us 1. And then we also put v0 equal to 0 and x0 equal to 0. And that means that when we put it up here, we are going to get 1/2 of n times v1. And this is equal to f0 times b divided by 2 pi. And then I get a cosine of 2 pi x1. So when you fix x1, then you know the final velocity. And this is the answer. So then what we would get now would be that v1 is equal to plus minus. And then we would have the square root of f0 times b divided by 2 pi. And then we have a cosine of 2 pi x1 divided by b minus 1 here. So this is a typical example on how you could apply the work energy theorem to find the velocity. So alternatively, you could actually have found the acceleration by dividing by the mass of the object, and then you could have integrated up, and then you would have got to something which would depend on time. But in this case, if you look at the problem we have, this is a problem where you have a force which is time independent. So we are mainly interested now in the velocity as a function of the position, which is the interesting variable here. So if we now look back a little bit to what we defined last Monday, when we looked at conservative forces, which lead to conservation of energy. And we haven't proved this. We are going to prove that on Monday, when we are going to bring back some of the mathematics about line integrals. And then we're going to prove these statements. But conservative forces, they lead to a very important thing, and that is conservation of energy. Which means that the total energy, if we now write it out, E, is now going to be given, and we write it in a very generic way, K for the kinetic energy. And then there is a potential energy, and we don't specify the dependencies here. It could depend on time as well, but we just leave it like this. So this is the potential energy. And this is obviously the kinetic energy. And what we have when we have a conservative force is that the time derivative of the energy with respect to time is equal to 0. So that means that what we say then is that the energy is a constant of the motion. Now, there's a very important thing, as we said, is that these conservative forces have a property that F is now something which depends only on the position. Then we haven't shown this, and we're going to discuss this in more detail on Monday next week. The other important thing is that the curl of the force is actually equal to 0. And then there is another thing which we can derive from this theorem about line integrals, which is going to be extremely useful for us in order to understand forces given a certain potential. So in many cases, we would be given a potential surface. And from that potential surface, we can infer the form of the force. And that's something which these statements which you're going to see now, I'm just giving them to you. But on Monday, we will actually show that mathematically that this is actually the case. So there's another very, very important statement, is that V is actually the gradient of the potential. So if we now assume that the potential depends only on the position, that means that if somebody gives us a potential, we can actually find the forces. Or if we know the forces, we can find the potential energy. And from that, we can actually develop our own intuition about a physical system. And you will see this repeatedly in this course here, again and again and again. So when we are solving the equations of motion of a specific physical system, if we have the potential energy and the kinetic energy, we can often infer a lot about the physics of the system based on the potentials. And this is what, in a certain sense, what physics is about. If you know the laws of motion and you can solve them, you can say how the system will behave under the influence of these and these potentials. So the underlying fundamental forces in nature, they have some kind of potential. And from that one, we can say, what is the physics which drives this specific system? And that's extremely important because that gives us a deeper insight about physics and the laws of motion and how the system will evolve. Now, the other thing we did on Monday was actually to show that the total momentum is conserved if we only have internal forces. So typically when we now write F, so this is the conservation of momentum. So if we now call this the total force acting on a given object, so this would typically be given by the sum from I equal N. And then we have all the individual elements of a given system. And that's given by the acceleration. And these forces here is something which we would now write out as an I of N. And this is the force which now affects one of the objects. And this force here, each individual object in the system has a external force. So this could be a potential it is moving in, an external potential, plus some internal forces, I, which we just wrote as an internal force. And this Fi, the internal forces, is now given by a sum over J different from I. So these are all the other objects. And this is given by some kind of force Fij. Now, one of the things which we showed on Monday, we did it for two particles, for N equal 2 and internal forces only. I should write and instead of this ampersand sign, and internal forces only. What we found in that specific case is that F of I, if we now sum up the sum of all the internal forces, and we sum over I equal 1 of n F internal. This is something which then we could show that sums up to 0. We looked at the case with n equal to 2. This quantity here, the sum over I equal 1 up to n equal 2 of the internal forces. So let me put on arrows here. That was now given by the sum over I equal 1 up to n equal 2. And then there's a sum over j different from I and up to n equal 2 here. And then we had an Fij. So for this specific case, this simply ends up being F12, the force from object 2 and force on object 1, plus the force on object 1 acting on object 2. And then since we could invoke Newton's second law, this is equal to 0 since we are using the third law. And this simply states that this is equal to F12, but with a negative sign in front of it. So this is something which we showed for a system which had only 2 objects. It's very easy to extend this to many particles. So that means that if we have many particles, what we would end up with then is something which looks like this. So we would just have a sum over F of I equal to 1 up to n. And we are still insisting on the internal forces on this particle only. So this would now simply be given by I equal 1 up to n. And then I would have a sum over j different from I up to n. And this would now include Fij here. Now, this is something which I can rewrite in terms of the following. So I can rewrite it as a half. And this sum here means that I'm summing freely over all the forces. But then I have a constraint with j different from I. So this is a constraint. And I can rewrite this as an Fij plus an Fji. So it's actually pretty easy to show that. And you can see that if you do 2 forces, not 2 objects, or if you do 3 objects, you can easily rewrite it like that. You can also rewrite it, since you have a double sum here, you can take away the factor of a half, and you can simply rewrite this as a sum now, which goes over I, and then I have a sum over j larger than I, and this runs up to n, and then I have Fij plus some Fji. And since now Fij is equal to minus Fji, then clearly this is equal to 0. That means, again, as we saw on Monday, that since the forces, and we have assumed that the masses don't change with time, the forces are proportional, are equal to the derivative of the momentum with respect to time. So we know that the total momentum, P total, is given by the sum over all the individual momenta. So we have mi times v of I, and this is something which we would write as I equal 1 up to n of P of I. And we know then that if we take the derivative of dP of dt total, that will be given by the sum over I equal 1 up to n. And we assume now that the masses do not change, of dVi of dt. And we recognize this again as the force. So this will be the force on a specific particle, the net force. And in our case, this net force is just equal to the internal forces. So we have made an assumption that there is no external force. So if we only had internal forces only, what that means, forces only, what that means is that dP the derivative of the linear momentum is actually equal to 0. And this is what we showed on Monday. So I'm just repeating some of the things which we had on Monday. So these are very important relations when we do science. And if this is the case, if you have a problem where you only have internal forces, then you know without having done any calculations, you don't need to do it. You just say, I know with internal forces only, the total force is equal to 0. And that means that linear momentum is conserved. So we say then that linear momentum is a constant of the motion. Linear momentum is a constant of motion. But we have to be careful, because in case we have some external forces which are acting on the system, this is no longer the case. So if, however, if the force on a single particle, this net, is equal to some external force plus the internal forces, then the total force, F total, is going to be the sum over all the external forces. So the internal forces would sum to 0, but these one would not be summing to 0 unless you have a special force which sums to 0. So if you're placing an object in some kind of potential, and these objects interact. So suppose you have an electron which moves in a harmonic oscillator, and it sees another electron, and they interact via the electrostatic forces. There will be forces between the electrons, which in sum will cancel each other, but there will be a potential which keeps the electron moving, or the electrons moving inside this potential break. So that means that the electrons, in that specific case, they will have a net force which is different from 0. So these are things you can quickly analyze. So just keep these things in mind. They're very simple properties. If you look at the forces, you say immediately, okay, the system is only affected by internal forces. Okay, then linear momentum has to be conserved if it's also time independent. And if it's time independent and the curl is equal to 0, then you also know that the total energy is conserved. Now, there's another very important quantity which you will often see, which deals with some fundamental symmetries. This is the angular momentum of the system. And under some circumstances, this is a quantity which is also conserved, in particular when you only have internal forces. So let's prove that before we go back to the exercises which we plan to discuss on Friday, exercises 5 and 6. So I just wanted to take another 10 minutes and just look at the conservation of angular momentum. So now we've conserved internal linear momentum, we've looked at energy, and then there's another quantity which is the angular momentum. And that's also a very important property when we are studying physical systems. If the system is rotating, then clearly we want to understand whether angular momentum is something which is conserved or whether it can change. So if it changes, you would have a torque acting on the system, and that will definitely change the properties of the system, how it evolves with time. So if we now repeat this exercise, there's a definition of angular momentum, we just call it L, and that is given by R, and it's the curl of the position and momentum, and this is again given as M of R multiplied with V. And we know that this quantity here is something which, when we look at it now, what it means is that the angular momentum is a vector which is perpendicular to the plane which is spanned by the position and momentum. So you know that the curl gives you a vector which is perpendicular to the plane spanned by the two vectors you're calculating the curl of. So this is a kind of picture you can have of the angular momentum. Now, the thing we are interested in now is to see whether the angular momentum actually is a conserved quantity. So we are just asking ourselves, is this the case or not? So what we simply do now, and now we need some of these properties from the exercises which we did in homework number 1. Remember, we took the time derivative or the derivative of the curl. That was one of the exercises we had. So we can use that feature again. And in this specific case, what we get now, if we look at dl dt, we just use the chain rule again. So we get then mass, and then we have a derivative of r with respect to time, multiplied with v, and plus r multiplied with dv and dt. So if we look at the first quantity, what do we have in that quantity? If you just look at, we have dr dt multiplied with v. How can we rewrite that one? Yeah. Yeah, velocity times cross velocity, right? So the first term, if you look at that one, this term here, this is just the velocity cross the velocity, right? So if we look at that one, this becomes equal to m times v cross v. This is interesting. And then we have r, and then we have the mass multiplied with derivative of the velocity. That's just the force, right? So if you look at the first term, what is the curl of a vector with itself? That becomes a very interesting number. Anyone who remembers that? 0. Excellent. So this is actually equal to 0. So this quantity here is equal to 0. And now you see another thing which is interesting here. If you look at the term with the position and the force, what would happen now if the force is parallel to the position? Think of these as two vectors. Again, the hint goes back to the first term, because then v cross v, they have to be parallel, right? So if the force is parallel to r, it means it's just a constant times something. So what would we get then? 0 again. So if we now can write the force as something which is proportional to r, then the linear momentum will be conserved. And this is actually what happens when we have a conservative force which depends only on position. So let's look at that. So here, what we can say now is that we can, if r is parallel to f, that means it's just a constant times r, then this is equal to 0 as well. And then we would have energy conservation. So if not, then the system has a specific torque. So then we have defined the torque. So this is actually equal to the torque of the system. And this tau is given by r times f. And this is different from 0. Then angular momentum not conserved. Angular momentum not conserved. So what I want to do now is the final manipulation and show that if we have a force which depends on r, it obviously depends on the type of force, we can actually show then that angular momentum is going to be conserved. So if we look at the gravitational force, and one of the things you can do actually when you look at the Earth-Sun system, you can show analytically and also numerically that angular momentum is going to be conserved. And that's an extremely useful property. And this is something which is actually in Kepler's laws. So for those of you doing astronomy and astrophysics, this is probably something you have heard of already. But we are going to demonstrate this. And this is a pretty neat property. And that's due to the properties of the forces. So the mathematics here is not, how to say, intimidating. I hope not. So if we look at L here, and we have a collection of objects, and what we are going to say now is that we have isolated objects. So we have n isolated objects. So the total angular momentum is the sum of all the angular momenta of the different objects, L of I, like this. So the other letter is supposed to be a lowercase l. I hope you can forgive me my handwriting. I have never applied to medical school, but I realize that I may be fulfilling some of the requirements. Okay, so when we take the derivative then, what we end up having to do is to take the derivative of all these angular momenta. So we would have a d dt of L of I. And we know that this is nothing, when we now collect all the terms, this will be nothing but the torques which we have, Ri multiplied with F of I. Now, if these are internal forces only, so we have isolated objects, and normally when we say we have isolated objects, we mean normally that we have only internal forces. That's another way of saying that we have internal forces only. So if you're given a system of isolated objects, it means that they're just interacting among themselves, unless you specify these objects moving in some external potential, but then they are no longer isolated. So that means that I can rewrite this in the following way. So I have an I equal 1 up to n, and then I have my Ri, and this is multiplied with a sum over j different from I up to n, and then an Fij, like this. And I'm going to use the same trick as we had before. And I'm going to rewrite this in terms, so I'm going to sum freely here. So I'm going to sum over I and j, but with the constraints that I is different from j. And you can see that when you do this, when you're summing freely, you can rewrite this as an R of I multiplied with Fij. So now you're, in a way, you're double counting that, and that's why you have this factor over 1/2. So not that one, but multiplied with Fji. It's easy to see this, and if you're a little bit uncertain, I mean, just write it out for 2 particles only, and then you will quickly see that. So you can rewrite this now if you now remember that this one is equal to minus Fij using Newton's third law. So we can rewrite this one in terms of 1/2, and then we have a sum over Ij, and then j different from I, and we are going to have Ri minus Rj, the distance, the relative distance between 2 particles, and then multiplied with Fij. And now comes the important thing. If you think of the gravitational force, which we mentioned last week, so if Fij is proportional to Ri minus Rj, what would you say then about the derivative of the total angular momentum? It's 0. So if that's the case, then dl dt is equal to 0. And if you look back at the gravitational force, which we had on, we actually rewrote the gravitational force between the Earth and the Sun. So we had something like a G of Ri of Rj. And that is proportional to the masses of Mi, Mj. There's a gravitational constant. Let me just skip it. So something like this, and then we had divided by the absolute value of Ri minus Rj cubed, and then we had Ri minus Rj as a vector. So the only thing, the force goes like 1 over R squared, but what I did was to multiply it with a unit vector. So if you look at that one, that's the gravitational force. And then we have a force which actually has this property. And if I use the gravitational force then I would expect that angular momentum is conserved. So these are some simple manipulations we can make. I hope you don't find the math too intimidating, but this shows you now that angular momentum is conserved as a constant of the motion if our system has a force which is proportional to the relative distance between the objects we're looking at. If that's the case, then we have some fundamental properties of a physical system, which we can simply say, this is what it should be. And all observations on gravitational forces and many of the fundamental laws of nature, they do actually conserve these properties. So it means that if you have such a force, you don't need to run a calculation, or rather you would run a calculation to check that your codes are functioning properly. But you know the answer. So this is extremely useful. And what I wanted to do now after this is actually to take a look. So I wanted to use the rest of the time here to a little bit prepare the discussion for Friday and say a little bit about the exercises. And I wanted to focus on exercises 5 and 6, because the other ones, some of them are in Taylor, so it's just a manipulation of mathematical expressions. But exercises 5 and 6 are a little bit more important, because the way we are going to write the program becomes important for the rest of the semester. And our hope is that if you can, get the code working properly and understand how to set it up, then you can reuse this again and again for most of the problems. Because most of the problems deals with you analyzing the system, finding the forces, and then using an integrator for solving differential equations. So unless you have any questions about these things about linear momentum, angular momentum. And as I said, on Monday, we are going to derive these fundamental properties about conservative forces and see mathematically from the theorem of line integrals that the forces which have this property, they have a curl which is equal to 0, and they have a force which is defined by the gradient of the potential. Okay, so let's now look at exercises 5 and 6. Exercises 5 plus 6. Now, in this case, what you have is a system where you have defined an initial position at the time t0, which we just call r0. And this is given by some variable, the height, and it has a vector j here. And t0 is normally set to 0. And it has an initial velocity, v of t0 is equal to v0 of x times I plus v0 of j times of y. So the system is under the influence of two forces. So we have the gravitational force, which is given by G. In our case, it's minus m times G, and it's multiplied with a unit vector in the y direction. And then we have this additional force, which is some kind of air drag or air resistance. And this term now, compared to what we did in class last week, is given by some constant. And then we have V times the absolute value of V. And in our case, this quantity, just to remind you of that one, the absolute value of V is actually given by Vx squared plus Vy squared. Now, in this exercise, so this is the way you would set up the system. But in this exercise, we are just going to set the system so that's falling in the y direction only. Now, if you want to solve this in the x and the y direction, it doesn't have an analytical solution. And the reason why it doesn't have an analytical solution is due to this term here. Because Vx and Vy are connected. But in this exercise, we specialize to an object which is just falling in the y direction, to object falling in the y direction only. So what we would have then would be something like this. So you have your object, and you have the gravitational force, G here, and this is now simply minus mg times j. And then we would have this drag force, which is acting in the opposite direction. So the only thing we need to think of now is a little bit about what we define as negative and positive directions. So in our case now, what we would have is that this would be plus a d times simply v squared. And this will be multiplied with j here. So that acts in the opposite direction. Then we can find the acceleration in the y direction. And now the only thing you need to be a little bit careful about when you do this, acceleration would be minus g, and then we can put a plus minus, and that depends on whether the object is falling down or going up. So this is divided by m. So we can relabel this quantity here as a quantity we call d tilde. So this would be minus g, and you just need to think a little bit about in what is your positive direction and what is your negative direction. So in the y direction only, so in exercise 5, we would have ay equal to minus g, and then it's going to be a plus a d, and it's going to be Vy squared. And this is the same as dVy dt. In the x direction, in exercise 5, if you now look at the case an object falling in the y direction only, this is simply equal to 0. Else, if you're looking at an object in the x and the y direction, then you would have to specify this object here with this d tilde, and it's going to have a v of x, and this is multiplied with a absolute value, and this is multiplied again with the unit vector in the x direction. So if you now specialize to one direction only, you can integrate this analytically because there is no dependence on Vx from Vy and vice versa. So that means that, and if you go back to the slides from week 3, you will find the solution to that one, but also in Taylor. So I'm sneaking in this kind of you having to read Taylor. because you find the solution to the problem in Taylor in chapter 2. So what I'm going to do now is simply to give you the solution, and you will find it in the slides, but what you will find is the following. So you will find when you integrate, because you can separate the variables, is a v times a constant vt times tan h, and then you have minus g times time divided by this constant v of t. And this v of t is a natural velocity or system-dependent velocity, and this is divided by g, the square root of g divided by d. Then you can also find the final position, and this is the one we are going to compare our numerics with. So we have a vt squared divided by g. It gets a little bit breezy, a little bit ugly expression here. This could be in a cosine, so I'm just setting it up. You don't need to integrate this if you don't want to. You can actually use Mathematica or symbolic Python. But if you want to, you can also integrate it up. So you can use the tools which you want to. But the important thing for us now is that we have an analytical result we can compare our numerical results with. And then we can start analyzing and see whether this makes sense or not. So if we now go back to the code, and this is the things we want to give you as a kind of homework for Friday, is actually take a look at the code and start thinking on also on how you can simplify it and how you can add something to the X direction. So the code is general. So you can write a code which solves the equations in the X and the Y direction. But when you want to test it against the analytical solution, you can only test it for a solution in the Y direction. So if we go back, if you use the last minutes to actually take a look at the code here, let's just do that. And there's a Jupyter notebook, which you can download from the exercise. So the first thing you could do, let me just increase the fonts a little bit. Let me just bring up. So you can choose different variables here. You need to specify these. So when you're running it in the exercise 6, you can specify initial velocities, you can specify the initial height and so on. You need to set up a delta t, a time step. You need to set up arrays which contain velocities, positions, and accelerations. So if you look at this exercise 6, I call this a kind of straightforward or brute force way. If you scroll down a little bit, you will see that I have defined these different quantities. I fixed the t final to 1.4, which is one of the things you have to figure out why it could be 1.4 or another value. I define this constant. And here, I'm not making this in a very elegant way, as you can see. So I define an array for the velocity in the X direction, in the Y direction, and similarly for the position in the Y direction and the X direction. So you can make this more compact. And this is one of the things I want you to think about, because when you go to more complicated systems, this becomes a little bit clumsy because you would just have a copy and paste. And it's so easy to make errors when you copy and paste. So Python has this functionality that you could define a vector in more than one dimension and as a function of time. So these are things we want to discuss a little bit more in detail on Friday. But this serves as a kind of skeleton. Actually, in a sense, it's a solution to the problem. But we want you to use that as a kind of way to think. So we tend to give you recipes, but you should feel free to scratch what we have and write your own code, right? But this is a kind of a very simple-minded way. And now what we have made here is a general program, and we put the initial conditions for X equal to 0, velocity and position. In that way, nothing happens in the X direction. And when you plot your results then, so here you have the acceleration, and this is simply the expressions which we put on the whiteboard, which are plugged in here. And then I'm updating the velocity in the x direction, position in the x direction, y direction, and so on. And then I have the analytical solution, which I'm comparing everything to. If you now look at the plot here, you would clearly see it, and we are coming back to this on Friday. You see now that in this specific case, due to the initial condition, nothing happens in the x direction, right? So everything is 0, as it should be. And then you can compare, you have a general program which runs in the x and the y direction, but you can compare it to a special case where it only falls in the y direction by changing the initial conditions. So you have already a general purpose program which you can use according to different initial conditions. And then you can start reasoning, right? So what we have here agrees with what you expect. It looks like Michigan, right? Pretty flat. Or since I come from Norway, the Danes always tease us because we are the mountain hillbillies and Denmark is flat. So we always say this is Denmark seen from the sea. Or Netherlands seen from the sea. Oh, by the way, you can't see the Netherlands from the sea because it's below sea level. And that's perhaps because the Dutch people are the tallest people in the world. I don't know if you knew that. And the tallest people in the US are the Dutch immigrants from places like Holland. So when you're born below sea level, you really have to stretch it. Okay, guys, that was a small digression. So these things are the things I want you to look at till we meet on Friday, and then think about how you can make this better, more general. But now you have the basic framework. And the rest of the semester, the kind of programs you're going to develop, they're going to be lookalikes of what you see here. We're going to make them a little bit nicer with better methods, more stable methods, and so on. But essentially, this is the kind of machinery we use when we study mechanics problems. I'm going to stop the recording